This is Lecture 6A for Calculus 2, giving two examples for computing the area between curves. In this first example, we're just given two curves. F is x squared and g is 3x. And we want the area between them from 0 to 5. Okay, so this is written, as you remember from the other lecture. Let me get the pen. This would be the integral of f minus g, an absolute value, dx, and the limits are set 0 to 5. Now, to evaluate this, we must break this up into regions where f is greater than g and f is less than g. So we can determine this algebraically. You can think about it, or I'll just go ahead and show you graphically on the next slide. The red curve here is x squared, and the blue, of course, is the line 3x. Okay, between 0 and 3, f is less than g. And from 3 to 5, f is greater than g. Right? So the curves trade places at x equals 3, and that's how we break up this integral. So 0 to 5 becomes 0 to 3 and 3 to 5. Then we look in each region. When I look in this region, we want the absolute value of f minus g, but here the absolute value of f minus g would be equal to negative quantity f minus g. So we can remove the absolute value signs, but we must precede the integral with a negative. In this region, f is greater than g, so the absolute value of f minus g is just equal to f minus g, and that's what we see here. The reason I'm showing this example is it's so easy to think, oh, positive, negative, positive, negative. That's not necessarily the case. In this region, we started out with f less than g, so the first sub-integral is preceded by the negative sign. All right? And remember, I used a convention that I leave the order f minus g the same under the integral sign. This is not necessary, but this is what I do. And then I precede it by either a change in sign or leaving the sign alone. You can work this out, just a power rule. The other types of problems that you see for the area between curves is when it's stated the area enclosed by these two curves, and then no limits are specified. So the area enclosed by two curves, what you have to do then is find your limits of integration, and those limits of integration are the points of intersection of f and g. So I'll demonstrate that here with an example where f is 12 and g is x squared. Right. I'm going to show you that on a picture on the next graph. So here's a graph of these two functions. So the function f was just the constant 12. So that's shown here in blue. Right here. Okay, this is f. Now the g function was x squared. That's shown here in red. So what we want is this area enclosed between these two curves, and these limits aren't specified. Before they were in the other cases. Here, we need to find these two numbers, and then we integrate between these two numbers. You can see where they are graphically, but this is found algebraically. It's found algebraically by equating f and g. So you set f equals g, and you find the values of x for which this holds. So this is what we do. To find where these curves intersect, we set f equal to g, solve the equation. We find there's two values of x. x1 is 3, and x2 is minus 2 times the square root of 3. Those become the limits of integration. And you can carry this out. It's not an issue using the power rule. Okay, so what we had before was just the area between two curves where the limits were specified, where a and b were specified. In those cases, we're taking the absolute value, so we have to divide a and b up into regions where f is greater than g and regions where f is less than g. Okay, and then take the absolute values and adjust the signs. The other kind of statement here is when it's the area enclosed between two curves and the limits of integration aren't specified. To find them, set f equal to g, solve the equation, and find the limits. Find the limits of integration that way.